In the last video, we defined double integrals and we talked about double iterated integrals. And in section 13.2, we're going to show that the double iterated integrals are the key to evaluating double integrals. But I want to emphasize one thing, and I can't overemphasize it, that when you write down a double integral of a function over a region R, you are talking about a limit of a summation. You kind of forget to have a limit bit. You're adding. Double integrals add. Right? The idea is that if this were your region R, and you draw a little piece of area dA at a point x and y, then what the integral does, it says, I'm going to evaluate the function at this point, that's that. Then I'm going to multiply by this little piece of area, and I'm going to add over all the little pieces of area in that region. So it is a summation. Clear. Do not ever forget that. All right. What the book does, it says, suppose, I'm not going to talk about all of it. It says, it starts with a rectangle that looks like this. This is A, this is B, this is C, and this is D. And what it does, it divides up this rectangle into a whole bunch more smaller rectangles by drawing vertical lines and horizontal lines. And it would talk about, at this point, call it x sub I, y sub j. So you've got I subdivisions this way, or n subdivisions this way, m subdivisions this way. It would call this delta xi, and it would call this delta yj. And it says, suppose then we divide up. Right, we've got this definition of a limit summation here, where we have to divide the little pieces of area, and the little pieces of area are rectangles. And so we evaluate the function at this xi, yj, we multiply by the area of the rectangle, and then we proceed to add. And it talks about two ways of adding. It says, add, first of all, vertically, and then after you finish that, add horizontally. Or start horizontally, and after you do that, then go vertically. All right? And it proves then, by doing that, that this double integral of this function f of x and y can be evaluated by the following double iterated integral. Or this double iterated integral. It proves that. And I'll leave you to read that if you wish, the proof. But it proves that you can evaluate this double integral over this rectangle by doing vertical lines and horizontal lines, making rectangles, that you can use this double iterated integral or this double iterated integral, reverse direction. Both of those will give you the answer for the double integral. I want to accept that, and then I want to interpret what's going on here so that if it is not a rectangle, then I can adapt very quickly. Because I'm never going to give you a rectangle, right? It's always going to be some region bounded by some curves. So we need to go from this very simple idea of a rectangle to more complicated regions. I'm going to suggest is that we think of it this way. I'm going to do the rectangle again, but I'll see how to graduate to non-rectangles when I finish. I'm going to think of this rectangular division. I'm going to think that we've got all these vertical rectangular lines, we've got all these horizontal lines, right? Dividing it up into rectangles, and there's a position x and y. And this rectangle has width dx that way, and width dy that way. Right? So that's at position x and y, not very clear. Right? There's that rectangle. So instead of having the delta xi and the delta yj, all right, we've got dx and dy, reminiscent of what you did in first year when you're doing applications of the definite integral. You didn't write delta xi's or delta yi's. You wrote dx's and you wrote dy's, doing the same kind of thing. So what happens is, my little piece of area now becomes dy times dx. The area of that little piece is dy times dx. I go and evaluate my function at xy. That's where this little rectangle is. And now I start to add. All right? Since y is first, that means I'm going to be integrating in the y direction. I visualize that as integrating over all of the little tiny rectangles that stand inside this vertical strip. I have to tell it where to start. It's going to start here when y is equal to c. When is this summation going to stop? Up here when y is equal to d. So I envisage this as a summation of that over all the rectangles in a vertical strip. And now the outer integration adds over all of the strips. The first one here is at A, and the last one here is at B. And that's exactly this one here. All right? Alternatively, I say, yes, do the same division, but if you want to integrate with respect to x first, and then y second, visualize adding them over all the rectangles that stand in a horizontal strip. What is this limit going to tell you? Where does the horizontal strip start? A. Where does it stop? B. Outer in respect to y now adds over all the strips. First one's in C, and the last one's in D, and that's that one there. All right? So I'm interpreting then what's going on this. I'm interpreting everything I see here in terms of summing, but now in a special way. It's either over vertical strips, the inner integration, or over horizontal strips, if the integration with respect to x. And then the outer integration adds over all the strips. So inner integration inside the strip. Outer integration over all the strips. Right? So let me show you a different picture and how we graduate from this idea to any shape whatsoever. Suppose this is the region that I want to integrate over. I want to talk about a double integral over this region of this function equal to. What do? Same thing I did there. I visualize dividing their area up into a whole bunch of little rectangles, up with dy that way and dx that way. That position x and y. What do? I multiply the function by the area of the rectangle. I could at this point write either dy dx or dx dy. Not sure which, I will know in a minute. Now, what I integrate first, that means I'm now going to add over all the rectangles in a strip. I'm going to choose vertical strips. And then we'll talk about horizontal strips after we're finished. Right? So that means indeed I'm going to integrate with respect to y first. So the inner integration is over all the rectangles inside a vertical strip. Now what you got to visualize is this is not just one strip, it's any strip. Any of the vertical strips in this side, I got to visualize integrating over any one of them. And what's this limit going to tell me? This limit is going to tell me where the strips start. Over here, they all started along here. Not here. The vertical strips are starting along this curve, and that's where y is equal to g of x. Upper limit told me over there where the vertical strips stop. And here, they all stop along here, therefore, h of x. So I've now integrated inside this vertical strip. I now add, with respect, by integrating with respect to x, over all of the vertical strips. I put here, where's the first one? It's at A. Where's the last one? It's at B. So if I do that double iterated integral, I will get the value of this double integral. Now think about, suppose you decided, I like to integrate with respect to x first. Right? So you start it, you say, okay, no problem. F of x and y, dx dy. You say, now let's add. What does this limit tell me? Right? It says, I'm now integrating this way. My x integration is over all the rectangles inside a horizontal strip. And what's this limit supposed to tell me? Where do all the horizontal strips start? And now you've got a big problem. I can see someone going from here to here. I can see some going from here to here. I can see some going from here to here. I can see problems over here too. All of them, they don't all start on the same place. Don't do it then. This is not a wise choice. Okay? Getting the idea? Let's put down here symbolically what the limits mean. And I think you're going to agree with me, or getting the idea, that if you don't have a good diagram here, you have a major problem on your hands of figuring out what these limits are. You've got to be reasonably good at drawing. And that makes me say, and when it comes to later when we triple integrals, and we integrate over volumes of space, the problem is even more compounded. If you don't have a picture, you're going to be stymied. So we need good pictures. So let's write here that if we use a double iterated integral with respect to y first, x second, to evaluate a double integral. What does this limit mean? By the fact we're integrating y first, that means we're going this way. This is position, or let's not say, where each and every vertical strip starts. Vertical strip starts. That's your interpretation for this limit. Up here, where stops. Where each and every vertical strip stops. Outer limit, position. First, vertical strip. Up here, position. Last, vertical strip. That's what we were doing in here, right? Lower limit, where the vertical strips start. Upper limit, where they stop. X limit, first one, last one. All right. So there's our interpretation. And if you turn it around and do a dx dy, the only difference is you replace the word vertical with horizontal. All right, let's do some specific examples. I'll give you a function, I'll give you a region, and we'll at least set up the double iterated integrals that are possible. And I may leave you to finish the integration, but I want to concentrate on the setup. Suppose I gave you double integral x squared y cubed dA over the region R, where R is bounded by y equal x squared plus 2, and y is equal to x plus 4. So R is defined that way. One thing you should notice, because I may forget to mention it later, you're going to be given the integrand, and you're going to be given the region, and they have nothing to do with each other whatsoever. I can write anything I want here, and I get any region I want here. There's no connection between them. I have to tell you the function, and I have to tell you the region. Let's draw the region. We have y is equal to x squared plus 2. That's a parabola opening up, shifted up 2. Then we have a straight line that crosses at 4, and it's got a slope 1. So there's my region in there. That's what we're integrating over. All right? I presume some point in this problem, I'm going to need that guy, and I'm going to need this one. So let's get it now. I believe this one is -1 and 3. That works there. That works there. What about this one? 2 and 6? How does that work? 2 in here gives 6, and 2 in, yeah. All right? So there's the coordinates of those points. All right. Decision time. We're going to divide the region up into double integral x squared y cubed dA equal to. We're going to divide it up into tiny rectangles, and I recommend that you draw rectangles, right? People refuse to do that. Can often go wrong if they don't. All right. So I'm going to, here's my integrand. I'm going to divide into rectangles. dy dx, dx dy. I'm not going to fill that in until I decide. Do I want vertical or do I want horizontal strips? Answer, clearly, I do not want horizontal strips. Some of them would start on the line and finish on the parabola. Other ones would start on the parabola and end on the parabola. I don't like that. But if I chose vertical strips, they all start on the parabola, they all end on the line, I can get away with one double iterated integral. You can do it the other way, but you'll have to do 2 double iterated integrals. That's the choice that you make. I like dy dx. Adding, therefore, this limit, right? We're now adding over all the little rectangles standing in a vertical strip. Where do all the strips start? They all start in the parabola when y is equal to x squared plus 2. Upper limit, where do all the strips stop? They all stop on the line where y is equal to x plus 4. Now I add over all the strips by integrating the x direction. This limit tells me, where is the first vertical strip? -1. Where's the last vertical strip? 2. So if I evaluate that double iterated integral, I will get the value for the double integral. All right? Let's do at least one step. All right? What we should do is we should anti-differentiate with respect to y. X squared, y to the 4th, and then we will substitute x squared plus 2, and we will substitute x plus 4, and we will integrate with respect to x. So if we substitute, we could pull out the 1/4, interval then -1 to 2, up. Putting in, we will have x squared times x plus 4 to the 4th. Then we will have minus x squared times x squared plus 2 to the 4th dx. That we will have to do. I don't want to do that, right? I do not, and I have to. I would have to multiply that out. I would have to multiply that out, and it's going to be messy calculations. But we know where it's going now, right? Got the idea then? Now you're probably prompted to ask me the question, when I finish this, what does it mean? Suppose I get the answer is 53/4. What does that mean? Answer, I can't tell you. cannot tell you until I know what this means. You tell me what that means, and then I will tell you what the integral of it means. All right? And that we will see when it comes to applications, which are coming shortly. We'll be talking about almost all of the applications of integration you had first year. You had area. You had volumes of solid revolution. You had fluid pressure. You had centers of mass. You had moments of inertia. We will do all of those again. You also had work, but that's going to wait till math 3. And you had lengths of curves, and that's got nothing to do with areas and volumes or integrating over an area, so we don't do those ones. But those other 5, we will all do them again with double integrals, and they will turn out to be far, far easier than they were in first year. So don't ask me what this number means when I get it until you tell me what that means. Then I'll tell you what the integral of it means. Second example. Evaluate this double integral over region R of x plus y dA, where R is x minus 3 squared plus y squared less than or equal to 9. All right. Now, in doing this problem, I'm going to do what we always do. I'm going to draw the region, and then I'm going to think about what it means, what this double integral stands for. So, region. We've got ourselves a circle centered at 3 and radius 3. So we're integrating over that circle. That's our region R. All right? Now I would like to think about breaking this up into 2 pieces. As this plus this. All right, whoops, another integral sign here. All right. Now, because let's think about this one first. I can actually interpret that. You're taking a little piece of area at position x and y, and you're multiplying by y. There's the y. What does that represent? That's first moment. You could think of this as being the first moment of this circle around the x-axis. All right? Put that aside for a second. I want to think about that some more when I come to here. Think about this one in the following way. Do you agree that for every little piece of area that I have in the top half of the circle, I have a corresponding piece down here, and it's got a y. That y is precisely the negative of this y. Now remember that a double integral is a summation. You're taking this little piece of area, multiplying it by that y, taking this little piece of area, which is the same as that one, multiplying by this y, and that one will cancel that one. And since there's everybody up here has a counterpart down here, that guy is 0. Do this. Think about this every time. In fact, I had an email the other day from a person in Math 3 that they were doing something with integrals. It happened to be a triple integral. And she said, how did you get rid of that term? I just ignored it. And it was exactly this reason. I said to her that you've got, this is an odd function of y, and you've got symmetry around the x-axis, therefore the integral is 0. She said, oh, I forgot that. All right? Be on the lookout. It can save you a lot of work. All right, now back to this one. What does that represent? You're now multiplying the little piece of area by x. I could interpret this as first moment of area about y-axis. That's its physical interpretation. First moment of this region about the x-axis. In fact, because I'm an expert on first moments from first year calculus, I could say, hey, the center of mass is right here. All you have to do is concentrate it all there and multiply by 3. So we could say it's equal to 3 times the area of the circle, which is, that's it. There's the answer. No integration required. All right? But let's suppose you said, I don't like that. I don't remember that. Let's set up an integral, all right, for this guy instead. Well, I would still take the option in saying that the integration of him over him is the same as integration of him over him. Integrating over the top side of the circle is going to give you the same as integrating over the bottom side of the circle. So let's replace it with twice the integral r1 of x dA, where r1 is simply not that, it's only the top. That, I think, will make the life a little easier for me. All right. So we see now that, here we go, 2 x dd. Do you want to divide this semicircle up into horizontal strips or vertical strips? You're going to make your little rectangle. Are you going to integrate this way or that way? I think I like this way. If I do it this way, I'm going to have to solve this thing for x in terms of y. I don't like that. All right? All right, so we'll say we're going to integrate with respect to y first. So we'll have a dy, and we will have a dx. This limit is going to tell us where all of the vertical strips start. Where they start along the x-axis, where y is 0. Upper limit is going to tell me where they all stop. They stop on this curve. I would have to solve this with an equals for y. The square root of 9 minus x minus 3 squared when I solve it. All right? Outer limits. This one here tells me first vertical strip, 0. Upper limit, last one, what's this? 6. 6. Right? So I'd have to evaluate that. All right? I don't like that, all right? If you integrate this with respect to y, you're going to get xy. And in for the y, you're going to put this, and you're going to get the 9 minus x minus 3 squared. And now you're going to be using a trig substitution to finish that problem. All right? So do that. I'll leave you to finish it and see if you get this same answer. Now, I said to you a few minutes ago that there's 2 distinct parts to every double integral, the integrand and the region. All right? The region dictates the limits. Conversely, if I put limits on an integral like this, you can decide what the region is. And I want to emphasize that with the following problem. I'm going to ask you to evaluate the following double iterated integral. 0 to the square root of 4 minus x squared, 0 to 2 of 4 minus y squared to the 3 halves, dy dx. So I didn't start with, perhaps I did. Perhaps I started with a double integral, and I subdivided it up into rectangles, and I came up with this double iterated integral, and I said, I got a problem. I do not want to integrate this with respect to y. If I did, I'd have to put y is equal to 2 sine theta, and it's going to be a mess. Why? Yuck. But wouldn't this be easy to integrate with respect to x? Agreed. Because there's no x's there. The antiderivative would be x times that. Maybe then I should switch from a yx integral to an xy integral. Maybe that would help. Well, if I'm going to do that, switch around, I need to see the region. So let's take these limits and convert back to the region and then switch the strips. All right. This is saying we took vertical strips. This limit is telling us where they all start. All the strips start when y is equal to 0 along the x-axis. This limit is telling us where they all stop. They stop when y is equal to the square root of 4 minus x squared, which is the same as x squared plus y squared is equal to 4. Oh, they all stop on a circle of radius 2. That's where they stop. These limits are going to tell me where the first and last is. The first one is x equal to 0 here, and the last one is x equal to, that's right there. Ah, so there's the region. The region is that quarter circle. Let's consider now switching from vertical strips to horizontal strips. All right, so let's do that. So we will have the integrand 4 minus y squared to the 3 halves dx dy. X limits. We're taking horizontal strips, right? Lower limit where all the horizontal strips start when x is 0. Where do they all stop? They all stop when they hit the circle where x is equal to the square root of 4 minus y squared. Outer limits, integrates back to y. First one y equal to 0, last one y equal to 2. So there's the problem if I switch the order of integration, switch from vertical strips to horizontal. And we said that this was very easy to integrate. The antiderivative is x times 4 minus y squared to the 3 halves, into which we'll put 0 and the square root of 4 minus y squared, and then in respect to y. And you can see that helps tremendously. Putting in x equal to 0 is gone. And if you put x equal to this, that's the same as this. You're going to end up with 4 minus y squared squared. I can handle that. So switching the order of integration was a terrific idea. So I always realize that that's possible. If you don't like to integrate this with respect to y, consider changing it, right? So that finishes the idea of replacing double integrals by double iterated integrals. Next time we'll talking about